So now we're going to use a 10 UF, and we're going to put it in the place of where the old capacitor was. Positive side, long end. Negative side, short end. On the other side. Get in there, there. This one's a little different. I didn't put it in H, I put it in G. But we're still good. So it's a lot less capacitance in there. And let's plug in our circuit. And there we go, we have light. And now we disconnect it, and notice almost instantly that went out. So 10 UF is a lot less energy storage. So let's see if we can put on our little LED. See if that makes a difference. Putting that in 12H to 12D. Come on, get in 12H. There we go. 12H to 12D. The more you use the more you use these breadboards, the easier it would be to put components in there. Okay, so once again we connect, and we get our little light, and we disconnect, and it's almost instant. That 10 UF can't even power this for a little period of short period of time. But in our next lecture, when we deal with transistors, which are switches, the 10 UF capacitor will keep the LED on for a while, because it is powering the switch, which takes a lot less current and voltage than it does to power the LED. So the power from the LED will be coming from the battery, and the power to keep the switch open, to keep the LED on, will actually come from the capacitor. Okay, I'll do one more close-up of that so everybody can see. And I'll turn it in case there's a wire in the way. Shut off the LED. And that's our breadboarded circuit. Okay, now another thing we discussed during the lecture was power supplies. Now, we have been using a battery to power our projects. But let's say we wanted something a little more permanent. We didn't want to keep buying batteries, or not only buying batteries, but having to recharge them, and the voltage wanes and it has funny effects on our circuit. We wanted a steadier current and voltage to go through. We might take, like, this is a power supply that I hacked. It's only 9 volts. And if you look here, I want to make sure you can see this. It says we have our input is 120 volt AC, 60 hertz, 11 watts. That is our input. If you're over in Europe, it'll probably say 120 volts. But what we're really concerned with is our output. It says 9 volt DC, 500 milliamps. So using this, we can power our little circuit here fine. It doesn't matter that our little circuit is only taking 12 milliamps. We can power it fine. We can power up to 500 milliamps with this. Of course, I probably wouldn't use it for anything over, maybe 350 milliamps, because you don't want it to overheat. But that's what this looks like. And most of these things have those listed. Here's another power supply. This one is input is AC, 100 to 250 volts, 50 to 60 hertz. So this one I can use here or in Europe, but my output is what I'm concerned with. I have DC, 5 volts, and 400 milliamps. Hopefully you can read that for the output. And this is actually a USB connector. So anything I power on a USB I could power here, but certain things like my camera needs at least 500 milliamps, and this won't heat up, and it won't. My camera won't even accept it. My camera won't make a connection with it because it's not enough for the camera. And we also discussed that Christmas decoration that I had made. And this is a lot more complex. Let me turn it right side up. So this is a lot more complex because my output voltage and then my max current changes. This is a variable. I change this little thing here, and I can change the voltage, and it changes what I can use. Now I have it set for 9. I have a 9 volt in there. And so if we use this chart, of course we have our input, which is 100 to 240 volt, 800 milliamp, 50 to 60 hertz. That's the fluctuation of the AC from positive to negative. But if we look here, we're concerned with our output really. Output is selected by a changeable slot. That's this guy here. So, and then we have our output voltage. And if we go over to 9, and then we look down to the next row, we see we can use 3 amps. Max current amps. So at 9 volts we can use 3 amps. At 5 volts we can use 4 amps. We can get 4 amps out of this power supply. At 12 volts we only get 2.5 amps out of this power supply. So basically by reading these you can see, you know, what you can use to power it. So you can hack these guys and use them in all your projects. Not only that, now that you're armed with that information, if you look at the other side of a product, it tells you what its input is. I've seen very few products that don't actually have it. Wherever they plug their little power plug in the back, as long as you get the voltage right and the milliamps of the power supply is greater than the milliamps of the circuit or whatever it is that you're going to power, you should be able to power fine. So if you lose an adapter for, say, an electronic device, if you look on that electronic device, you should see, you know, let's say the input 12 volts, 500 milliamps. Just go find a power supply that has 12 volts and at least 500 milliamps. It could be like that one I just showed you and have 2 amps or 2.5 amps, but it will power that just fine. Your only problem is getting a connector that fits on the other end, so you may have to cut off the connector. Like I did with this one, you cut off the connector and then solder another connector onto it and use shrink wrap to keep these two separated. But we'll do more of that review in the future. It's actually good information to have. And I think that about wraps up this lab. If anything I've missed, send me an email, post some comments. Anything you'd like to see. We will get into the microcontrollers. Our next step is, it's already posted for the PNPs and NPNs. Then we're going to do a lab for them, the NPNs and PNPs. Then we're going to do a lab for, we're going to do a brief lecture and lab. I think I'll combine that into one, for an N-channel MOSFET. NPNs and PNPs come in different flavors, and N-channel MOSFET is one of those, and it allows us to power, we're actually going to power a motor with it. The PNPs we're using, they're rather small, and I wouldn't really power a motor with those, but I would use an N-channel MOSFET to actually power a motor. And then after that, we're going to build our first real circuit. We're going to build a night light, where the light comes on when the light goes out. And for that, and I should probably put that in the notes below, I didn't mention in the variable resistors, there's another type, an LDR, light dependent resistor, also known as a photocell. Here's 2 of them here, and their light is dependent on their resistance is dependent on the amount of light they see. And actually I could show you that quickly since we're all set up here. So this is our LDR, or photocell. It's hard to find this product under LDR, light dependent resistor, although that's what it is. A lot of people call them photocells. So, okay, once again, there's no polarity on this resistor, so it doesn't matter which side we hook up. Let me switch over to resistance. Now, I have 2 of them here, a small one and a big one. I have no idea what their range is. So let's actually start low at 200, and let me connect this guy. and we've got a 1. Now let's cover him up and make him dark. And we still got a 1. So we need to go up. 2K, we still got a 1. Let's cover him up. And we still have a 1. So let's go up again. There we go. Now with the light we're seeing now, we have 3.3K. We're on 20K. So the light we're seeing now is 3.3K. Now if we cover him up, he goes to 1. That should tell you something. That should tell you that in the dark, he provides more resistance. In the light, he provides less resistance. So let's bump him up to 200K. And let's cover him up. So we're bumped up to 200K, and as you see, it's 3.3K, 3.2K on there. And then we cover him up, and he's a 1. So his resistance goes way up. His resistance could go up well beyond. But let's give him a little light. See, there's 100,000. I'm actually giving him just a little bit of light. There's 100,000. So the darker it is, the more he goes up. And he went over 200K. Let's go to 2 million now. 2 million ohms. And we'll see we're 0.004 or 0.003 when I'm not causing some light, when I'm not removing some of the light from him. But you see how his resistance varies. So we can actually, and we'll do this with the microcontroller, we're going to use all kinds of stuff to create different kinds of sensors. This will be a light sensor to tell you how much light. And we can determine how much light. So now let's cover this guy up. Completely dark as I can make it. And we've got 300,000 ohms. 360, 370, 400. I've got 400,000 ohms. Let's call it 400,000 ohms in complete darkness. Okay, now let's take this smaller one. And smaller doesn't necessarily mean it's a smaller range, or I'm guessing it is in this case, but it doesn't necessarily mean that. You always have to test these. So let's put this guy into the bit bucket. Oh, here's another trim pot, another variable resistor I have. I think we'll take a quick look at him too, because these labs are helpful. Once again, no polarity on this guy. We're up at 2 million ohms, so let's connect either end and see what happens. And we have light, and we're going to, wow. So with light, this guy, with the light source, this guy is reading 7K. So if we move down to 20, he's 7K with light. Let's take trusty Phoenix light. This guy right here. Always have a light handy. And now we put this on him. Now he's down to 900 ohms. 0.9. Let's kick up the light on our Phoenix flashlight, which we can do. Okay, he's super bright now, and he's down to about 200 ohms. About 200 ohms on that. Now, if I put him into total darkness, I can tell he's actually more resistive than the last one, the bigger one. Let's bring him up to 2 million, and let's put him in complete darkness. And he's above 2 million ohms. So he completely shuts everything off in complete darkness. Okay. So those are our photocells, our light-dependent resistors. I do have a thermistor around here. I'm not sure where it is. Okay, so here's another potentiometer. We're going to connect one here and the other to RC. Oh, that's another thing I meant to show you. Let's turn down this. So we're at 1 right now. Let me get a screwdriver out. Give me a second here. Actually, I think I could do this side as well. Okay. Yeah, it's a Phillips. So, basically, when I turn him all the way down, I've got 16 ohms. Now if I turn him all the way up, he goes beyond that. So he goes beyond 200 ohms. So he's about 205 ohms all the way up. Now if I take A and connect it to B, I should get the full resistance. See? A to B is the full resistance. And it doesn't matter whether I turn it or not. It's now a... it's no longer a... it's no longer a variable resistor, but a fixed resistor. And back to... Now, if I... Let's say... Okay, so that's... If I put it back to C, we see he's up there, 206 ohms. And if I put him from C to B, he's almost at 0. And if I turn it backwards, and let's go halfway, he's at 114 ohms. And now if I connect over here to the A again instead of the B, he's at 95 ohms. Let's see if we can come right in the middle. 98, 100. Okay, let me check over here now. 108, 109. So that's how that works. I remember pointing that out in the lecture. Between the legs, we have A, C, and B. A to C, C to B, and A to B gives you the full resistance. I think that's it for now. Thank you for watching, and